Welcome to the DX Today podcast, where you guess facts and no hype.
Thanks for having me back.
Oh, we are thrilled to have you here with us for today's deep dive. If you are listening to this right now, you are probably already well aware that the architecture of artificial intelligence has been, well, completely upended over the last 24 months.
Yeah, entirely rewritten.
Right. You follow the tech, you see the headlines, and you know we are long past the era of the basic generative text box. But what we are looking at today goes far beyond simple feature updates.
We are exploring a massive stack of sources today.
Massive. We're talking tech market reports, exclusive engineering sessions from the NVIDIA GTC 2026 conference.
Some really dense academic papers on edge AI architectures.
Yeah, and some incredibly sobering clinical ethics research coming out of Baylor College of Medicine. So, the mission of our deep dive today is to take all of these highly specialized, seemingly disparate pieces of information and synthesize them into a cohesive map for you.
Exactly. We are tracking the migration of AI from a cloud-bound unimodal query engine to an entity that is natively multimodal.
Physically embodied in robotics.
Deployed directly at the edge of our hardware networks and fundamentally agentic.
And we are going to strip away all the marketing jargon. We want to look at the actual mathematics, the data fusion techniques, and the infrastructure overhauls making this reality possible.
And critically, we're going to unpack the profound ethical and consent-based challenges this creates when these ubiquitous systems intersect with, well, your personal biology.
Yeah. This is really about mapping the new operating system of the physical world.
That is.
Okay, let's unpack this. We have to start with the fundamental shift in how these models process reality. We are looking at a recent Decrypt article covering OpenAI's new O series.
Specifically the O3 and O4 mini models.
Right, and the defining characteristic highlighted across all their technical documentation is the word omnimodal.
Omnimodal, not multimodal.
Right, because the industry has thrown around the term multimodal for a few years now. But the documentation is drawing a hard line here, insisting these models are natively omnimodal from the ground up.
Which means they are ingesting and processing text, image, audio, and high frame rate video simultaneously.
They are not using the old Frankenstein approach.
Oh, the Frankenstein approach. Yeah, where you route an image through a vision API.
And turn it into a text caption.
And then feed that text into a language model.
Exactly.
That distinction is the entire ballgame, really.
Yeah.
And the 2026 Guide to Multimodal AI from TileDB provides the architectural breakdown of why that matters. The Frankenstein approach you mentioned is essentially a pipeline of unimodal models.
Which is inherently lossy.
Very lossy. When you force a vision model to translate a complex, emotionally charged image into a text string, you lose an immense amount of high-dimensional data.
You lose the nuance.
Right. But the TileDB source explains that natively omnimodal architecture completely bypasses that translation bottleneck. It utilizes shared embedding spaces.
Shared embedding spaces.
Yeah. Rather than keeping audio data, visual data, and text data in separate siloed databases, the model maps everything into a single, unified mathematical space.
Which means the model isn't translating a picture of a dog into the word dog.
No, it's plotting the visual pixels of the dog and the audio waveform of a bark into the exact same high-dimensional coordinate system as the text.
Wow.
The TileDB piece breaks this down into three critical phases: the input module, the fusion module, and the output module.
Right. The modality encoders are extracting features from all these different data streams simultaneously.
So if the model is analyzing a live video feed of a human speaking, it is pulling the acoustic features of the voice,
the visual features of the facial microexpressions,
and the semantic meaning of the words at the exact same millisecond.
It's all happening at once.
And it's the fusion module that actually unlocks the reasoning capabilities. TileDB details how this shared embedding space allows for different types of fusion.
Like early fusion.
Yeah, early fusion, where raw data features are combined almost immediately. Then you have late fusion, where independent predictions are made and then weighed against each other.
And hybrid fusion.
Right, which dynamically routes the data depending on the task.
Right.
The practical outcome is that the AI can evaluate conflicting data streams and deduce context.
Give me an example of that.
Okay, so if a user says the word fine, a standard language model registers agreement.
Sure.
But an omnimodal model hears the elevated pitch and microtremors in the vocal acoustics. It observes the tightening of the orbicularis oculi muscle in the video feed.
The eye muscles.
Exactly. It fuses those embeddings, and it concludes that the word fine is actually an expression of severe frustration or sarcasm.
It's performing contextual reasoning across sensory domains.
Precisely.
And the sheer velocity at which this omnimodal reasoning is advancing is staggering. I mean, the Decrypt reporting highlights a study out of the University of California, San Diego, where GPT 4.5 was put through a rigorous, modern Turing test.
And we are not talking about the old ELIZA chatbot tests from the 1960s.
No, not at all, where the judges were easily fooled by basic reflective questions. The UCSD researchers prompted the model to adopt a highly specific, complex persona.
An introverted, internet-savvy young adult.
Yes, it utilized contemporary slang flawlessly. It managed conversational pacing and effectively simulated emotional and perceptual reactions to the judge's queries.
The metric that stands out in that UCSD study is the 73% success rate.
73%.
It managed to convince human judges that it was a biological human nearly 3/4 of the time.
That is wild.
But what is perhaps more indicative of the market's current state is how quickly that achievement was overshadowed. As Decrypt noted, just weeks after GPT 4.5 made headlines, we saw the rollout of GPT 4.1.
The naming conventions have entirely decoupled from linear logic at this point.
Oh, completely. But the technical specs are what matter. GPT 4.1 introduced a verified 1 million token context window.
A 1 million token context window fundamentally changes the utility of the model.
It does.
For context for you listening, you are no longer limited to pasting in a few articles or a chapter of a book. With 1 million tokens, a developer can upload an entire legacy software codebase, complete with all its dependencies and documentation.
And ask the model to identify systemic vulnerabilities.
Exactly. You can upload the entire corpus of a company's legal contracts spanning a decade and ask it to find contradictory indemnification clauses.
It changes the model from a conversational partner into an instantaneous, omniscient auditor of massive data sets.
And concurrently, we have GPT 5.4 being deployed to compete directly with xAI's Grok 4.20.
Pushing the parameter counts into realms that require entirely new data center architectures to even train.
Right.
What's fascinating here is how this scale and omnimodal perception act as the foundational prerequisites for agentic AI.
The shift to agents.
Yes. The Decrypt source touches on this transition, and the TileDB guide explicitly defines the boundary line. Multimodal AI, no matter how advanced, is ultimately a perception engine.
It observes.
It observes, it maps data to a shared embedding space, and it waits for a user to prompt it for an output.
But agentic AI
Takes that omnimodal perception and couples it with autonomous planning, multi-step execution, and real-time environmental feedback.
It shifts the paradigm from a tool that answers questions to an autonomous worker that pursues goals.
Exactly. The distinction is critical. If you ask a perception-based AI to analyze your corporate cloud spending, it will generate a brilliant summary showing you are overpaying for AWS server instances.
Which is helpful.
But an agentic AI, given the same request and the necessary permissions, will analyze the spending, determine which server instances are redundant, draft an email to the engineering lead for approval, wait for the response, automatically execute the API calls to spin down the redundant servers, and then adjust the monthly budget spreadsheet.
It is autonomously executing a multi-step workflow across different software environments.
And the market data confirms that this isn't just a theoretical framework being tested in closed beta. It is actively displacing legacy software.
We see that in the Grandview research report on the multimodal AI market size and share for 2030. They single out speech and voice data as the fastest growing segment of this agentic revolution.
Because voice provides the lowest friction interface for human-computer interaction.
Right, and when you put an agentic engine behind a voice interface, you completely bypass graphical user interfaces. You don't need to open menus or navigate apps anymore.
The Grandview report provides a highly tangible example of this with GoTo.
The massive Indonesian tech conglomerate.
Yes, they recently integrated Dira into their GoPay application.
And Dira is not a customer service chatbot that links you to an FAQ page.
No, it is a fully agentic fintech voice assistant. A user in Indonesia can simply speak into their phone in natural language, asking to transfer a specific amount of money to a friend and pay their utility bill.
Just talking to it.
The agentic AI parses the omnimodal input, navigates the internal architecture of the fintech app, authenticates the user, executes the transfer, pays the bill, and confirms the transaction.
It operates the software on behalf of the user.
The Dira example illustrates the immediate commercial viability of software agents, but it also highlights a profound limitation.
What's that?
Dira and agents like it are trapped within the digital ecosystem. They can manipulate APIs, they can alter databases, and they can send emails. but they cannot alter the physical environment.
Right.
If the goal is to build truly generalized artificial intelligence, the system must be able to perceive, plan, and execute tasks in the unstructured, chaotic physical world.
It needs a physical embodiment,
Exactly.
which is the perfect bridge into the physical realm. When we look at the DigitalOcean overview on vision language action models, or VLAs, we start to see how this intelligence is being downloaded into hardware.
VLAs are fascinating.
If a large language model is a disembodied brain, a VLA is a brain connected to a central nervous system, eyes, and limbs.
The DigitalOcean piece provides a crucial history of how we arrived at this architecture, because robotics historically operated on an entirely different paradigm than AI.
Right. It requires looking at the lineage of robotic control systems. For decades, robotic automation was strictly task-specific and entirely rigid.
If you look at an automotive manufacturing plant from the early 2000s, those robotic arms were marvels of engineering, but they possessed zero generalized intelligence.
They were programmed with hard-coded spatial coordinates.
Exactly. Move exactly 45 degrees, extend 12 centimeters, apply a weld, retract.
If a car chassis was misaligned by a single centimeter,
The robot would weld thin air or crash into the frame. It could not perceive its environment or adapt to novel situations.
so the shift began with the introduction of robotic transformers.
Specifically, the RT1 and RT2 models discussed in the DigitalOcean overview.
Researchers realized that the massive semantic understanding these models gained by scraping the entire internet could be translated into physical reasoning.
Think about it. A model that has read 10 million articles about kitchens and watched a million videos of people cooking already understands the semantic concept of a spilled cup of coffee.
Right, it understands that coffee is liquid,
That glass breaks.
and that a sponge is used to clean it up.
The breakthrough was mapping that massive pre-trained internet knowledge directly to robotic actuation.
And that mapping process evolved rapidly into systems like RT2X and OpenVLA.
The challenge was that early robotic datasets were incredibly narrow. A model might learn to operate a specific robotic arm in a specific Google research lab, but that policy wouldn't transfer to a different robot in a different facility.
So what was the solution?
As outlined in the sources, it was the creation of the OpenX embodiment dataset.
OpenX embodiment.
It was an unprecedented collaborative effort across dozens of institutions to pool robotic telemetry data. They gathered data from single arms, bipedal robots, quadrupeds, and mobile manipulators.
Wow.
By training the OpenVLA models on this massive, diverse dataset, the AI learned generalized physical control.
It learned how to translate its semantic intent into universal physical actions, regardless of the specific hardware embodiment it was occupying at the time.
Exactly. And we are seeing heavy capital deployment aimed at making these foundation models universally accessible,
Yeah, the DigitalOcean source heavily features Physical Intelligence's Pi series.
focusing specifically on their Pi Zero model.
Right. This is an initiative dedicated to open sourcing general-purpose foundation models, specifically tailored for robotics.
The objective is to provide the underlying operating system for adaptable, unstructured environments.
Not a pristine laboratory where everything is perfectly lit and organized.
No, a chaotic warehouse floor where boxes are dropped, or a residential kitchen where objects are constantly moved.
But to achieve that level of adaptability in unstructured environments, the model has to possess an innate understanding of physics.
Which brings us directly to the exclusive sessions from the NVIDIA GTC 2026 conference. NVIDIA's entire strategic pivot right now is heavily anchored in what they term physical AI.
Right. The centerpiece of their announcements in this sector revolves around the NVIDIA Cosmos open world models.
Because training a neural network to understand physical laws, gravity, friction, material deformation, object permanence, is computationally punishing if you try to do it purely in the real world.
Because if you put a multi-million-dollar prototype robot in a real kitchen and tell it to learn how to crack an egg through trial and error, it is going to destroy the kitchen.
Short-circuit its own servos.
Yeah, and burn through months of real-time experimentation before it gets it right.
Precisely the problem NVIDIA is solving. The Cosmos World Foundation models act as hyper-realistic digital twins of the real world.
Digital twins.
They allow developers to create physics-accurate simulations where the AI can practice a task millions of times at accelerated computing speeds.
So the AI can attempt to crack a simulated egg.
Apply too much force, shatter it, adjust its virtual torque matrices, and try again thousands of times a second.
NVIDIA calls this the simulation to real pipeline.
Right. The model learns the optimal physical policy inside the simulation, and once it has mastered the physics, that exact neural policy is downloaded directly into the physical robot.
Which can then execute the task flawlessly in the real world on its first attempt.
It's incredible. And we don't have to look to the future to see this physical multimodal AI generating massive financial returns. It is already happening at industrial scale.
Yeah, we have a dense but vital paper from Atlantis Press that analyzes smart logistics decision-making.
Specifically focusing on JD Logistics' deployment of multimodal data fusion.
This paper takes all the abstract concepts of omnimodal reasoning and applies them to the brutal realities of global supply chains. JD Logistics abandoned the old method of relying solely on GPS and static routing algorithms.
Instead, they built a system that fuses highly disparate data streams in real time. The scope of the data ingestion is massive.
The paper details how the system continuously fuses 2-minute interval traffic updates.
5-meter precision vehicle positioning telemetry.
And over a year of deep historical delivery data.
It is not just looking at a map. It is analyzing the momentum of the fleet, the historical probability of congestion on specific arterial roads at specific times of day, and real-time environmental factors.
By fusing these distinct modalities into a single predictive engine, the system autonomously reroutes thousands of vehicles dynamically to avoid bottlenecks before they even form.
And the performance metrics cited in the Atlantis Press paper are staggering, particularly during high-stress periods.
They measured the system's efficacy during the Double 11 shopping festival,
Which is one of the most chaotic logistical events on the planet.
Using this multimodal fusion, they maintained environmental monitoring accuracy for their cold chain logistics to within plus or minus 0.5 degrees Celsius.
When a company is transporting highly sensitive pharmaceuticals or perishable organics, a temperature variance of a single degree can result in millions of dollars of ruined product.
Furthermore, the system achieved a storage and sorting efficiency that was 5.2 times faster than manual labor.
It cut average delivery times by an hour and a half.
And compressed their overall loss rate from 0.8% down to 0.3%.
A 0.5% reduction in loss rate across a logistics network that handles billions of packages translates to an astronomical recovery of capital.
Huge, but the paper dives deep into the specific engineering hurdles required to maintain that precision.
Particularly the issue of signal degradation.
A major problem in fleet tracking is when vehicles enter interference zones. Driving through a 2-mile tunnel or navigating deep urban canyons surrounded by skyscrapers that cause severe multipath GPS errors.
If the agentic routing system loses the location data of 100 trucks simultaneously, the entire predictive model collapses.
Right. The Atlantis Press paper explains that JD Logistics overcame this using highly advanced statistical filtering, specifically focusing on Bayesian estimation and Kalman filtering.
These algorithms allow the system to maintain pinpoint accuracy even when the primary sensors go completely blind.
The mathematical elegance of these filters is remarkable.
Bayesian estimation operates on the principle of updating probabilities as new evidence arrives,
The system takes a prior,
which is the historical knowledge of how fast traffic usually moves through that specific tunnel at 3:00 p.m.
and continuously updates it with whatever fragmented sensor data it can still acquire, refining its prediction of the truck's location.
But the Kalman filtering is the true workhorse in these interference zones. It is a recursive algorithm that fuses multiple noisy data streams to estimate unknown variables.
So to put that in concrete terms for you listening, if a delivery truck drops off the GPS grid inside a tunnel, the Kalman filter doesn't just guess where it is.
It looks at the last known GPS coordinate.
It then takes real-time telemetry directly from the truck's internal CAN bus. The wheel speed sensors, the steering column angle, the accelerometer data.
It takes that mechanical data, compares it against a digital map of the tunnel's curvature, and mathematically calculates exactly where the truck must be.
Updating that calculation recursively hundreds of times a second.
It effectively maintains perfect visibility without needing a satellite connection.
It's an incredible application of edge-level sensor fusion.
But as you scale that level of continuous recursive computation across millions of delivery trucks, drones, factory robots, and smart home appliances, you run headfirst into a catastrophic infrastructure problem.
The infrastructure bottleneck.
Yes, you cannot route the data from a million Kalman filters and omnimodal video streams back to a centralized cloud server for processing.
The latency would cause autonomous vehicles to crash.
And the bandwidth costs would bankrupt the operators.
Which brings us to the core issue of how we actually power this new reality, the ArcSIF paper titled Edge Large AI Models. collaborative deployment and IoT applications attacks this infrastructure bottleneck directly.
The authors point out that the conventional cloud-centric deployment paradigm is fundamentally broken for physical AI.
Right, sending raw video data from a self-driving car's cameras to a server in Virginia, waiting for an inference, and waiting for the steering command to be sent back takes too many milliseconds.
The physics of the real world require local, instantaneous processing.
So the proposed solution is to push large artificial models, or LAMs, directly to the edge.
Meaning the massive neural networks must run locally on the IoT devices themselves.
But the immediate counter-argument is hardware limitation.
You cannot fit a trillion-parameter omnimodal model onto the localized silicon of a delivery drone.
Right. The Archive paper identifies the primary villain here as redundant computation.
When engineers try to compress standard monolithic AI models to run on edge hardware, they are forced to run incredibly inefficient sequential processes.
The authors use the example of an autonomous driving system.
A standard compressed model has to process the visual environment to perceive obstacles and then run a completely separate computation to predict the future trajectories of those obstacles.
It is looping through redundant mathematical operations.
Which spikes the processor's temperature, drains the battery, and introduces the very latency they were trying to avoid.
The researchers' technical fix for this is a total architectural redesign. They propose abandoning the monolithic model entirely in favor of a microservice-based framework.
Instead of one massive AI trying to do everything, the LAM is decomposed into discrete functional modules
that are deployed dynamically as microservices across a localized network of devices.
And to make this work, they utilize two advanced paradigms: mixture of experts, or MOE, and chain of thought, or COT reasoning.
Let's break those down. To understand the mixture of experts architecture, you have to look at how parameters are utilized.
In a standard dense neural network, every single parameter is activated for every single calculation, regardless of how simple the task is.
Which is a massive waste of energy.
And MOE architecture introduces a gating network. The model is composed of several smaller subnetworks, or experts.
When a piece of data comes in, say, a token of text or an audio waveform, the gating network rapidly calculates a probability distribution to determine which specific expert is uniquely trained to handle that specific data type.
It only activates the necessary parameters, leaving the rest of the model dormant, which drastically reduces the computational load on the edge device.
The Archive paper is very transparent about the limitations, though. They note that while MOE reduces computation, it introduces severe bottlenecks in edge environments.
If you were trying to schedule these different experts in parallel across highly heterogeneous edge devices,
say, an autonomous car that is trying to coordinate compute power with an older smart city traffic light,
the synchronization delays can be worse than the initial latency. If one expert node corrupts or drops its connection, the entire inference stalls.
The solution they developed to counter that synchronization bottleneck is fascinating. They pair the MOE architecture with chain-of-thought reasoning.
Instead of demanding a single massive output, the model breaks the problem down into a sequence of discrete logical steps.
But more importantly, they employ graph diffusion models to manage the deployment.
You can think of a graph diffusion model as an incredibly advanced logistics planner for data.
It maps out all the available edge devices as nodes on a graph,
Analyzes the network conditions and hardware capabilities of each node in real time, and diffuses the microservices across the optimal path of least resistance.
They actually validated this framework using the Qwen 2.57b instruct model.
They ran it against datasets of complex logical reasoning problems.
And instead of relying on one strong processor, they distributed the reasoning steps as individual microservices across a localized network of up to 10 different edge devices.
They proved that a swarm of weak, low-power IoT devices can collaboratively execute inference tasks that would normally require a massive, centralized server GPU.
Here's where it gets really interesting, because this massive shift from centralized monolithic models to distributed edge-deployed microservices is triggering an extinction-level event in the business software market.
We are looking at a comprehensive report from Artis on SaaS 2026 trends from AI experiments to production-ready platforms.
Their central thesis is brutal. The era of the flashy AI demo is entirely dead.
The Artis report confirms that enterprise buyers have completely lost patience with experimental AI.
In the initial wave of generative AI, every software company rushed to bolt a generic text-based copilot onto their legacy interface just to secure their venture capital funding.
But as corporate budgets mature into 2026, the demand has shifted violently toward durability, infrastructure readiness, and measurable return on investment.
The report explicitly states that architectural inertia is now a terminal competitive liability.
Companies that are clinging to monolithic software architectures simply cannot support the microservice-based, event-driven AI frameworks we just discussed.
The phrase that dominates the artist analysis is infrastructure beats feature velocity.
Enterprise buyers do not care if your AI can write a cute poem. They care about workflow orchestration.
They demand robust control planes and execution layers.
Because if an agentic AI is autonomously executing API calls and moving money, and that AI hallucinates or encounters a broken endpoint, the underlying business logic still has to function.
You have to have an event-driven architecture that can instantly catch the error, roll back the transaction, and alert a human operator without crashing the entire platform.
This infrastructure mandate is driving the explosive growth of what the report calls deep vertical SaaS.
In the previous generation, horizontal SaaS companies built generic tools like a basic CRM or a word processor and sold them to everyone.
Vertical SaaS goes deep into a single specific industry. And in 2026, enterprise buyers don't want generic foundational models. They want domain-specific AI workflows that guarantee a specific business outcome.
The artist report highlights the sports technology sector as a prime example of this deep vertical integration.
The sports tech example perfectly illustrates the difference between an AI feature and an AI outcome.
Right, a horizontal AI application in sports would just take a user's typed input about their weight and goals and spit out a generic text-based workout plan scraped from the internet.
The vertical SaaS platform artist highlights operates entirely differently. It utilizes edge-deployed vision AI.
It ingests raw, high-frame-rate video footage of a baseball player's swing directly from a smart camera.
It evaluates the exact biomechanics of the technique.
Applies highly specialized, proprietary scoring logic based on professional kinesiology.
Identifies unforced biomechanical errors.
And autonomously generates a personalized video curriculum of physical drills to correct the flaw.
It's not providing an insight. It is actively managing the outcome.
And to achieve that level of precision in vertical SaaS, the underlying data itself has to be treated as a highly engineered product.
The artist report is adamant that clean, versioned, and strictly governed data is the new underlying infrastructure.
You cannot train a domain-specific biomechanics AI on random YouTube videos. You have to have immaculately labeled proprietary data.
Consequently, enterprise procurement departments have made security, explainability, and AI governance absolute prerequisites.
If a SaaS vendor cannot provide a transparent lineage of the data their model was trained on,
or mathematically prove how their agentic AI arrived at a specific decision,
the enterprise will simply refuse to sign the contract. Explainability is no longer a theoretical academic concern. It is a hard go-to-market barrier.
which provides a stark and necessary transition into our fourth and final section today, the human element.
Right. It is one thing when we are discussing data lineage and explainability in the context of optimizing a baseball swing or tracking a delivery truck through a tunnel.
The stakes change completely when the data being ingested, fused, and analyzed by these omnimodal AI systems is extracted directly from your own biology.
We are crossing the threshold into the most intimate frontier of data collection.
The NVIDIA GTC sessions provided a glimpse into the industrial side of this, detailing the accelerating integration of AI into healthcare infrastructure.
They highlighted the transition from digital dry labs, which utilize high-performance computing to run computational biology simulations and protein folding algorithms, to autonomous wet labs.
We are seeing robotic VLAs operating continuously in sterile environments, autonomously conducting physical biological experiments, pipetting samples, and running assays based on the AI's own hypotheses.
And managing the massive data exhaust from these experiments requires specialized infrastructure.
That's where TileDB's concept of a trusted research environment, or TRE, comes into play.
A TRE is essentially an ultra-secure, highly governed data architecture that allows massive medical institutions to pool and query incredibly sensitive patient information.
They are combining complex genomic sequencing, transcriptomics, high-resolution radiology imaging, and decades of unstructured electronic health records into a single, unified database.
The goal, obviously, is to unleash omnimodal AI on this data to discover novel biomarkers and enable true precision diagnostics for rare diseases.
This raises an important question. What happens when these powerful omnimodal continuously monitoring systems leave the highly regulated confines of a hospital's trusted research environment and enter the unstructured, private spaces of your daily life.
The Texas Medical Center Library published a profoundly unsettling qualitative study in Digital Commons titled Ethical Considerations for Integrating Multimodal Computer Perception and Neurotechnology.
This paper forces us to confront the realities of ubiquitous biological surveillance.
The methodology of the study is important to note. The researchers didn't just poll tech CEOs. They conducted 66 in-depth interviews across a wide spectrum of stakeholders who are directly impacted by this technology.
They interviewed 20 adolescents who were actively managing conditions like severe anxiety, obsessive-compulsive disorder, or depression.
They interviewed 20 caregivers, 12 clinical practitioners, 12 software and hardware developers, and 2 hybrid clinician developers.
They were specifically investigating the ethical friction generated by deep digital phenotyping.
The evolution of digital phenotyping is central to their concerns. 10 years ago, digital phenotyping meant wearing a band on your wrist that counted your daily steps and roughly estimated your sleep cycles based on movement.
Deep digital phenotyping utilizes the omnimodal computer perception models we discussed earlier to continuously, passively, and aggressively monitor your state of being.
It is analyzing the acoustic tremors in your voice during a phone call.
It is reading the micro-expressions on your face through your laptop's camera.
It is correlating your GPS location with your typing speed and error rate on your smartphone.
It builds an incredibly dense, multi-dimensional matrix of your behavioral and emotional state.
And now the industry is aggressively pushing to integrate that external phenotyping with internal neural data harvested from functional MRIs, portable EEG headsets, and implanted deep brain stimulation devices.
The stakeholders in the Baylor study raised incredibly pressing concerns about this convergence.
One of the dominant themes that emerged from the interviews was the terror of what they called the Hoover vacuum effect.
A clinician explicitly warned that these continuous passive data collection systems act as ambient vacuums.
They indiscriminately suck up every sigh, every erratic keystroke, every spike in heart rate, and transmit it to cloud servers where it exists in perpetuity, irrevocably tied to the user's permanent digital identity.
The developers interviewed in the study shared that exact same apprehension, which is telling.
One developer drew a highly concerning parallel, comparing passive voice and acoustic recording today to the early days of commercial genome testing a decade ago.
When people mailed their DNA to a lab to find out their ancestry, they had no concept of what future algorithms would be able to deduce from that genetic code years down the line.
Similarly, if an Omnimodal AI is passively recording your vocal acoustics today, you have absolutely no way of knowing what a vastly more powerful neural network in 2030 might be able to diagnose or infer from that archived audio file.
The adolescent patients felt the weight of this permanence acutely. One young patient equated the continuous biological monitoring to posting an embarrassing photo on the internet.
Once it is uploaded, you lose all control, and it is stuck out there forever.
The perceived invasiveness of having a machine continuously evaluating your mental state in the privacy of your own bedroom is a massive hurdle.
But the most intellectually fascinating and troubling concept identified by the researchers is what they defined as the consent paradox.
The consent paradox brilliantly captures the absolute failure of our current legal and ethical frameworks to handle ambient AI.
Currently, consent is a binary point-in-time transaction. You click a checkbox on a terms of service agreement, and you consent.
But continuous omnimodal monitoring creates a tension between limited awareness and hyper-awareness.
Let's examine the limited awareness side of the paradox. If an AI is constantly running in the background, analyzing thousands of subtle biological cues, how can a user possibly give informed consent to the insights the AI might autonomously generate?
One of the caregivers in the study articulated this perfectly with a hypothetical scenario.
Imagine a caregiver is wearing a biometric smartwatch and has smart speakers in their home. The Omnimodal AI detects a sudden, massive spike in the caregiver's heart rate and galvanic skin response.
It simultaneously analyzes the elevated decibel level and aggressive acoustic signatures captured by the smart speaker.
The AI correctly deduces, logs, and perhaps even transmits the insight that the caregiver just had a severe, emotionally damaging argument with their spouse.
The caregiver in the study explicitly stated, "What if I didn't want to tell you that? That's none of your business."
Right. A person might consent to the hardware tracking their physical fitness, but they never consented to the AI mathematically deducing the intimate, private context of their marital deterioration.
That exact scenario completely alters the foundational dynamics of medical and psychological care. A clinician in the study raised a profound secondary effect. behavioral alteration.
If a patient is fully aware that an omnimodal AI is constantly tracking their lethargy, their vocal flattening, and their social isolation, and that this data is being packaged and sent directly to their therapist's dashboard,
Does that fundamentally change what the patient chooses to say during a therapy session?
if they assume the algorithm has already reported their depressive episode, they might stop voluntarily disclosing their feelings. They stop communicating.
Or on the other end of the paradox, they suffer from hyperawareness. They become intensely, paralyzingly anxious, constantly performing for the machine, modifying their natural behavior because they know an algorithm is perpetually judging their emotional stability.
The behavioral alteration is deeply concerning, but the study contains an ethical bombshell that pushes this conversation into entirely uncharted territory.
The researchers highlight that the frontier of this technology is no longer just external monitoring. It is the direct integration of neural data.
We are talking about hardware that interfaces directly with human brain tissue.
The study explicitly discusses how the field of functional neurosurgery is rapidly pivoting toward continuous data acquisition.
Devices manufactured by companies like Medtronic or NeuroPace are utilizing what is known as closed-loop neuromodulation.
To understand the gravity of closed-loop neuromodulation, you have to look at the mechanics of the hardware.
These are surgically implanted devices. They have electrodes resting directly on specific structures deep within the brain.
In a closed-loop system, the device is constantly recording the electrical firing of the neurons.
It analyzes those brainwaves in real time, detects an anomalous pattern, say, the neurological preamble to an epileptic seizure, or the localized hyperactivity associated with severe obsessive-compulsive disorder.
And it immediately delivers a targeted electrical stimulation back into the tissue to disrupt the pattern.
It is an autonomous, continuous feedback loop of recording, analyzing, and stimulating.
And we have to acknowledge that from a purely clinical perspective, this is a miraculous advancement for patients suffering from highly refractory, treatment-resistant conditions.
It provides a level of symptom reduction that traditional pharmacology simply cannot touch.
But the stakeholders in the Baylor study look at this capability, and they look at the rapidly advancing omnimodal AI we discussed in the first section, and they see a horrifying convergence.
One clinician provided a very stark warning in the text. They noted that right now, recording a single band of brain activity doesn't provide a comprehensive picture of a person's thoughts.
But the hardware is iterating rapidly, increasing the density and resolution of the neural recording.
When you take that high-resolution, continuous stream of raw neural data and you feed it into a massive edge-deployed neural network capable of finding patterns in millions of variables,
You cross an irrevocable line. The clinician explicitly stated, if we get to the point where you can deduce someone's internal state, it becomes an immense breach of privacy.
we are rapidly approaching a horizon where an algorithm, analyzing your brainwaves and fusing them with your vocal acoustics and facial microexpressions, will know you are experiencing a state of deep depression or profound anxiety before you have even consciously articulated that feeling to yourself.
And the terror expressed in the study goes even further than just unauthorized deduction.
Because, as we established, these closed-loop systems are not merely passive recorders, they have the capability to stimulate.
They actively alter brain activity.
The ultimate fear, explicitly voiced by the practitioners in the study, is the external control of internal mental states.
If a system can perfectly deduce your emotional state, and it has the hardware capability to physically alter the electrical firing of your brain to change that state,
Who dictates the baseline?
who decides what the correct emotional state should be?
The clinician warned that using technology to not only monitor but physically alter brain activity is a tool of unfathomable power.
And it requires an urgent, transparent, and entirely open societal debate about boundaries before the hardware becomes ubiquitous.
So what does this all mean? We have covered a massive expanse of territory today, and the trajectory is clear.
Very clear.
We started by looking at the foundational software architecture. We saw OpenAI's O-series models break out of the text box, natively fusing video, audio, and language to reason across domains and act as highly autonomous agents.
We then tracked that exact intelligence as it was downloaded into physical embodiments, with NVIDIA's Cosmos simulations and OpenVLA architectures giving robotic systems an innate understanding of physics.
We saw those systems actively managing real-world chaos, optimizing global supply chains, and predicting traffic patterns with breathtaking, mathematically proven precision.
We explored how the very infrastructure of the internet is being rebuilt to support this, pushing localized, edge-deployed microservices to devices to eliminate latency and rewriting the rules of enterprise software in the process.
And finally, we followed the logical conclusion of this technological vector directly into our own biology, where ambient sensors and implanted neurotechnology are actively fusing our digital exhaust with the electrical firing of our own neurons.
If we connect this to the bigger picture, it means that you, the listener, are currently standing at the exact intersection of perfect convenience and ultimate surveillance.
The architecture we have mapped out today is entirely agnostic. It merely processes what it is fed.
The exact same omnimodal AI and localized edge computing that can dynamically reroute a fleet of delivery trucks to avoid a storm or instantly isolate a genomic target to cure a rare disease is the exact same underlying technology that can passively ingest your vocal tremors, analyze your continuous biometric data, and autonomously predict your most private, unvoiced mental states.
The frictionless, agentic world we are building demands total visibility to function.
We are rapidly constructing an infrastructural operating system that is omnipresent, highly capable, and increasingly invisible to the end user.
It will fold your laundry, it will audit your code, it will balance your budget, and it will monitor the electrical stability of your brain.
And that leads to the final, necessary thought we want to leave you with today.
If multimodal agentic AI eventually becomes the ubiquitous operating system of our physical environment, and inevitably the operating system managing our own healthcare and biological data,
A system capable of perfectly anticipating our every need, diagnosing our every illness, and reading our every emotional fluctuation.
how do we protect our open future and maintain our cognitive liberty from an algorithm's inescapable perception?
When the machine possesses the computational power to map and alter your internal state, where does the machine's agency end and where does yours begin?
Something to mull over until next time. Thanks for joining us on this deep dive. Stay curious.